All right, we'll get started. And so today we're going to continue talking about generating random numbers. And last time we talked about the generating random numbers. And we talked about kind of the inverse transform method. And so, we covered the discrete case, and we'll take a look at the continuous case. So yesterday we did an example with the exponential distribution, and we can continue. So we'll try the, we looked at the inverse cumulative density function. We said the CDF maps basically x onto 0 to 1, and then so the inverse CDF will map 0, 1 to the domain of x, right? And with R, for some of these functions, this has, well, first of all, R includes a random generator function, which makes our life easy. Okay, so if you wanted random normal, you can do Qnorm. Okay, but let's say they got rid of the Qnorm function. Okay, but they kept Dnorm, Pnorm, and Qnorm. Okay, which one of these corresponds to the CDF? The Pnorm. The Pnorm, this is the CDF, right? This tells you what proportion, or what's the probability that x is less than some particular value, right? The probability that x is less than some value of x, okay? Which one is the inverse CDF? The Q, right? So this is the inverse CDF. So if I go to R and I say, we'll just come right here, and I can just say, okay, what's Pnorm? What's Pnorm of 0? 0.5, okay? And then I can say, okay, well, Qnorm of 0.5, that gives me back 0, right? So these are inverses of each other, okay? Pnorm of 1.96. You guys should know this, right? Pnorm of 1.96, what is this? 0.975, right? Okay. And then if I say Qnorm of 0.975, you get 1.96, or just about that, okay? Up to some rounding stuff. All right, and so here, using just Qnorm, we can generate random numbers. Even if somehow the Rnorm function on your computer got deleted, if you can do Runif, okay, we get, I should store this. I'm going to call this U, and I'll put parentheses around it so it prints out. Okay, so here's U. U is 0.787689. I can just plug this into Qnorm, and I can say, what's Qnorm of this? And coincidentally, it's also kind of 0.79. But this is a value from the random normal, okay? I could say, give me another U, and I plug that in, and this gives me another random normal. Give me another U. And these are all draws from the random normal distribution. Here, let me see. So sometimes we'll get this, and we just say, okay, well, what's Qnorm of that? Let me just see. So you can just plug in, when you do Runif. So let me just do Runif 1,000. Okay. And so these are all of my things, and I can just say Qnorm of these things, and we get this. And so I can do, give me a histogram of the 1,000 values, and we see it's uniform. And I can say, give me a histogram of Qnorm of those 1,000 uniform values, and we see this looks like the normal distribution. Okay, and so Qnorm works as our inverse CDF, and likewise, you know, anything else we can do, you know, Q exponential Q whatever. This then maps everything from 0 to 1 onto the normal distribution, or whatever distribution that we're looking at. Okay, you know, so what happens if I try to plug in Qnorm 1.2? Okay, it gives you an error, right? Or in this case, it gives you a not allowed, not a number. Okay, and that makes sense, right? Qnorm, if I do a negative number, or 0 would give me negative infinity, and a negative number also gives me a not allowed. Okay, basically a not a number. Okay, Qnorm 1 is that. Okay, and so Q of anything will give you infinity as well. Okay, and you know, Pnorm of negative 100, well, I guess that's 0, but negative 10 gives me something very small, Pnorm. That's interesting. Okay, yeah, tells me it's 1, but I guess we can't distinguish very much. Okay, I don't know what the upper limit on Pnorm is. Okay, well, I've never really tried to find the upper limit of Pnorm. Huh? Yeah, so, okay, but anyway, so so we can get an idea of how the inverse CDF functions work, or this concept of going from uniform 0, 1 and using the inverse CDF to generate a random number. Okay, I've already created homework 1 and I posted it. You should be able to take a look, and it's really just some basic exercises on generating some random numbers, and you're not allowed to use the Pnorm or the Qnorm, or the functions that make the assignment trivial. Okay, so and I don't know if you guys learned, maybe you did or you didn't learn, like the Kolmogorov-Smirnov test for, okay, you guys are shaking your heads, okay, or Shapiro-Wilk test for normality. Okay, well, all right, so these are just different tests that you can run to see if the numbers that you have, if they follow a distribution that you're expecting. Okay, and they're rather straightforward. I'm not going to try to explain how the math behind these tests work, but you know, so the Kolmogorov-Smirnov test, it's I'm sure I'm butchering those names there, but it's a non-parametric test. You create kind of an empirical cumulative density function based on the observations that you've observed, and then you compare that cumulative density function to your expected cumulative density function. And what the test does is it tries to measure the greatest difference between your empirical CDF and the actual CDF, and somehow it has numbers that will say, okay, based on this distance, we can assign a p-value of this type of thing. Okay, Shapiro-Wilk test is a test to see if your data is coming from a normal distribution or not. Okay, so you know, we don't get to appreciate how impressive the Qnorm function is. Okay, because in our computer we've taken for granted that Pnorm and Qnorm exists, right? Like we use Rnorm all the time, we use Pnorm all the time, Qnorm all the time, and because of that we kind of lose a little bit of how impressive these things are, right? Like sometimes when you stop and wonder, like, I have this device in my pocket that can tell me everything, like basically the collective knowledge of the entire world, that's impressive, but we get annoyed if it takes more than 4 seconds to load a page. But anyway, so we have Pnorm and Qnorm, and the math behind Qnorm is actually very difficult, okay? Because if we look at the normal distribution here, this is the PDF, okay? And the cumulative density function would be the integral from -infinity to whatever we're looking at of the PDF, okay? So let me just kind of, okay, this page, the point of this page is that inverse CDF for the normal distribution is hard, okay? Quite possibly impossible, okay? Maybe not even possible, okay? Inverse CDF method, because if we think about it, the CDF is going to be the integral from -infinity to x of, and let's just do standard normal, okay? Or we'll do a standard normal because then we can so the standard normal will be 1/2 pi e to the negative, what is it, x squared over 2? E to the negative x squared over 2, yeah. Okay. I guess this should be t if I put the x here. Okay, so this is the CDF, and then so we got to figure this out first. The Wikipedia says, okay, that's the error function of this thing, which is a little bit harder, and then it says, oh, all we do is we just do the inverse error function, but the error function itself is hard, right? And then now we have to find the inverse of the CDF. I don't think we could do this, right? And then okay, and this is difficult, maybe just possibly not maybe not even possible. Okay, and so for a while people had to think, how am I supposed to generate numbers from a random normal distribution? Okay, so how can we generate values from a normal distribution? And so one method that we'll talk about is called the Box-Mueller method. The Box-Mueller transform, or the Box-Mueller method here. Okay. And the idea here is we're going to kind of work in polar coordinates. Okay. So so polar coordinates, if we have something here, polar, our coordinates are in the form of r and theta, right? So we say here is we have r, and then this angle is theta, right? And then if we want to go from polar to rectangular or Cartesian, do you guys remember the conversion? X is r times cosine theta, and y is r times sine theta. Okay. And if we want to go from Cartesian to polar, how do we do this? let's so here I've got x. So Cartesian to polar, okay, r would be equal to what? The square root of x squared plus y squared. And then theta, what do we do there? We do arctan y over x, yeah? Or inverse tangent, you know. Okay, and so, you know, we're going to kind of deal in this scenario and say, we're going to say, okay, x and y, we're going to pretend that if x and y, so imagine x is normally distributed. So we're going to kind of work backwards here, all right? So we're going to say x is normally distributed, so it's going to look like this, okay? And then y is also normally distributed, okay? So its distribution looks like this, okay? Something. And so we have a you know, bivariate normal distribution showing I don't know if this picture makes sense here. Okay, so we have a, you know, bivariate normal distribution centered at 0 here. Okay, this is the idea here. So so we're going to say x is normally distributed and y is normally distributed also. Okay, but x and y are independent. Okay, so we're going to say these things are independent, and now we want to know, okay, if we get two dots, or I mean, if we pick an x at random and a y at random, okay, and we just plot it, okay, let's say we get a dot right here, okay, and we turn this into polar coordinates. Okay, so here we have an x and a y, so x comes from, you know, so x comes from the normal distribution centered at 0 with standard deviation 1. Y comes from the normal distribution 0 and 1. And we're going to say r is going to be this, and theta is this. You know, what is the distribution of r and theta? So x and y are normal with mean 0 and standard deviation 1. We're going to ask, what is the distribution of r and theta? Okay. Do we have any idea? Well, okay. Well, and this, so this is, we're going to try to derive or figure this out, okay? And I don't know if you guys learned this or not, so I'll just tell you, I guess. Like, have you learned about like joint distributions and the Jacobian, like the determinant of the Jacobian is used to map out like a transform from one set of variables to another set?
Is that from 32B?
Huh?
Is that from 32B?
I don't.
That was from 100.
Yeah,
I learned that in 100B.
It should be something, or it might be something that's covered in some 100Bs, but maybe not. And so Well, you know, we're not going to do like rigorous proofs here, but I'll show you some stuff. Okay, so we're going to try to figure out the distribution of r and theta, okay? And so keeping in mind some of this stuff, right? So if we have the, so in general, I don't know if this kind of, something like this. If we're going to have, we want the joint distribution of u and v, so this is the joint density of u and v over their PDFs of, okay, and this is being mapped from x and y, okay, the joint density of u and v over their PDFs, okay, and they are, you know, they are mapped from x and y. Okay, well this is going to be f of the joint distribution of x and y over x and y's PDFs multiplied by the inverse of the of this. Maybe familiar, maybe never seen this before. That's okay. All right. And then so this j sub g, this is the determinant of the Jacobian. Okay, and so for two variables, okay, functions of two variables, this is going to be the partial of function 1 with respect to x and the partial with respect to function 1 with respect to y, the partial of function 2 with respect to x, and the partial of function 2 with respect to y. Okay, and so when we do this, you get partial g1 over x partial g2 with respect to y minus partial, what is this, g1 partial y. Okay, so you get this thing. All right, and then so this is j sub g of this thing, and then you take kind of the inverse of this. All right, and so what we're going to do is we want to go from x and y to r, right? So we said r is, we're going to call this function g1, and g1 of is going to be x squared plus y squared, okay? And so if we do this, we did get partial g1 with respect to x. What is this? This is partial with respect to x of x squared plus y squared to the 1/2, and we get 1/2 x squared plus y squared to the negative 1/2 times 2x, right? And then so this just becomes x over the square root of x squared plus y squared. Is that okay? Did I mess something up here? Okay, I think I did this right. This is, I've worked some of these notes and I'm working off of a textbook here, so. And okay, and then we do the same thing for y, and we get partial with respect to y is going to be y over root x squared plus y squared. Okay. So this is these are the partials for g1, which is for our radius. Okay. And then we'll do the same thing, but for the theta. Okay. And so just to recall, when we take the derivative with respect to u of inverse tangent of u, we get 1 over 1 plus u squared. And I don't remember how that worked out, but this is from like calculus. So okay, so now we want to do so we said theta is equal, and we're going to call this function g2, and this is inverse tangent of y over x. All right, and so we're going to do with respect to x, and when we do all of this, we get what? We get 1 over 1 plus y over x squared times, with chain rule, negative y over x squared. And so we get negative y over and then doing the same thing, dg2 dy, we get 1 over 1 plus y over x squared, and then with chain rule times 1 over x. And so this gives us x over x squared plus y squared. Is that okay? Alright, and then so now we're going to take all of these things, and then we'll get our kind of our Jacobian, or j sub g of xy. And this, what was this? This was dg1 times dg2 dy minus dg2 dx dg1 dy. Okay, and so I have x over root x squared plus y squared times this one, x over root x squared plus y squared. Oh no, not root, just minus and then a negative something like this, and this gives me okay, and then it's over here. I can combine these, and I have x squared plus y squared over x squared plus y squared to the 3 halves, and this gives me 1 over x squared plus y squared to the 1 half, and ta-da, that's 1 over r. Okay, so this j sub g is 1 over r, and so when we go back and we want to get the inverse of this, this part just becomes r. Okay, so this part, so this is all our j sub g of x, y. Okay, and then so when we do the kind of the inverse of this thing, we'll get that. Okay. Maybe this is too much math, too much stuff. This is too much for my taste anyway. All right. So anyway, let's not lose sight of what we're trying to do. Okay. Again, we said x is a normal distribution, y is a normal distribution. We're just saying it's as if I said x is r norm 1 and y is r norm 1, and just give me 2 things, and then we're gonna plot this on the thing, and then we want to turn this into coordinate form. So what is what we're going to do is we're going to say, okay, let's figure out the joint density of r and theta, okay? And to figure that out, we have to we'll get the joint density of x and y, and then we have to figure out this function, which we spent all of this time just trying to work out this function, okay? And then once we have this function and we have the joint density of x and y, which is easy for us, we can then figure out the joint density of r and theta. Okay, so again, we want the joint density of r and theta. This is going to be equal to basically the joint density of x and y now times what we figured out, r. This is basically, this is f of u and v. This is equal to f of x and y times, and this part was the Jacobian function of x and y inverse. Okay, so the joint density of x and y. Okay, well this is easy because x comes from standard normal, right? X and y both come from standard normal. So the PDF of x is going to be 1 over root 2 pi e to the negative x squared over 2. Okay, so this is the PDF of x. PDF of y is the same thing, and so the joint density of x and y because x and y are independent, this is just going to be the product of this, right? So 1 over root 2 pi e to the negative x squared over 2 times 1 over root 2 pi e to the negative y squared over 2. Right. And just make sure that we know that's up there. Okay, and so this just becomes 1 over, what just happened? 1 over 2 pi e to the negative 1/2 of x squared plus y squared. Let me just make sure I'm doing this. E -1/2 x squared plus y squared. Did I mess something up? No, this is okay. Okay, and this is what we have. This is the joint density of x and y. What we're going to do is we're going to I've been a tiny bit sloppy. Is that all of this stuff? This only works actually kind of in the first quadrant here. Okay, so sorry, I apologize. We're gonna just, we should just limit ourselves to just the case where x and y are positive. Okay, so I should have said this earlier. We have limited ourselves to the case where x and y is positive. So technically the joint density of x and y, given that x is positive and y is positive, this is it's all of this, but it's just 1/4 of it, so we're going to multiply the whole thing by 4. Okay, so it's going to be 4 times this thing. Okay, so this gives me 2 over pi e to the negative 1/2 x squared plus y squared. Okay, and so now I'm going to try to wiggle in r and theta into this joint density. Okay, and so this is our joint density of x and y, and so using this as a guideline, we're going to try to get this. Okay, so we're going to say f of uv is equal to f of x times, now it's just r. And we have all of this, and so let me just copy this stuff over. So I have this. This is my joint density right there, and then we're going to multiply this by r. Okay, and so I'm going to just kind of replace some stuff in here. And so I've got 2 pi, and I'm going to just rearrange, move the r term over here, 2 over pi. And then here, this becomes e to the negative 1/2. And this term right here, this is r squared. Is that okay? Yeah, this is all right. So this is now our density of r theta. This is the joint density of r and theta. For when x is positive and y is positive, I should keep in mind. Okay, so just for a little bit of correctness, that's what we have. And then likewise, when it feels a little silly that this is what we did, because I said I should have kept this, and I multiplied it by 4, and we can do something similar for all of the 3 other quadrants, and they all end up getting the same thing. And so for all of x's, to get rid of this thing, we just end up dividing the function by 4. Okay, so f of r and theta, when we are not concerned about this, we divide this whole thing by 4, and we get 1 over 2 pi r times e to the negative. I'm going to just do r squared over 2. Okay, and this is for all x and y. Okay, and it feels a little silly, but technically we have to set up different conditions for each of the different quadrants, otherwise we run into problems. Like if you didn't do that and you were actually doing a real proof where your math instructor cared about all of these technicalities, we can't just jump from here to there. Okay, in this class I'm a little bit more loose with these stricter rules. So this is what we have. So this is our joint density of r and theta. Okay, now we can factor this apart. Okay, and we can say f of theta is the density for f of theta is just the function 1 over 2 pi, so it's just a uniform from 0 to 2 pi. Okay, so this is f of theta. And then over here we have f of r, the density, so this is the PDF for theta, and the PDF for r is r e to the negative r squared over 2. Okay, and apparently this has a name. I didn't realize this until I was looking at this textbook. This is called the Rayleigh distribution, which is the distribution of if somebody is aiming at a target, how far off are they from that target, and the distance from the target apparently follows a Rayleigh distribution. Yes?
Can you just explain how if you went from 2 over pi to 1 over 2 pi?
Yeah, because so this represents just one of the 4 quadrants. Okay, so technically, I'm always a little bit sloppy in my proofs, so that's why I'm terrible at actual math. So this part is the density for this section here, and basically, if we want it for all 4 quadrants, we're going to go from here and we basically just divide this by 4, pretty much, okay? Because this is, 4 times as concentrated, and this is, that's the loose term, kind of the intuitive sense. Mathematically, there's a little bit more work there, but we go from here to here, oops, by dividing by 4. Oh shoot, I am running out of time already. Okay. I shouldn't have messed with the thing. Okay, and all right. So this thing, if we try to work this into a uniform distribution, we actually can do this. And so the angle, the distribution of angle is uniform, and this part ends up having a this part has a Rayleigh distribution. Let me just kind of show you this picture here for the Box-Mueller transform. Okay, so what we're doing is we're going from 0 to 1, okay, and then here's the static picture. Okay, so we're generating. I'm sorry, I'm getting mixed up here. So what we've done is we've gone from 2 independent normal distributions, which when we kind of graph these out, kind of form all of these, concentric circles. And the angle that the line makes, it ends up being uniformly distributed between 0 and 2 pi, okay? And so we can kind of compress that into, by multiplying by a factor of 2 pi and getting it into 0 and 1. And then the distance ends up having this relationship over here. So we say, if we generate a uniform value between 0 and 1, we can get the theta angle by multiplying that value between times 2 pi, okay? And then the other value, okay, we generate the value between 0 and 1. We take the log of that, and if we multiply that by -2, this will give us the relationship to r squared. And so to get r itself, we take the square root here. And so this ends up just being the relationship. You generate 2 values on uniform 0, 1, and if you plug them in here, it's going to give you basically a set of coordinates that correspond to a random normal in the x direction and a random normal in the y direction. Okay, and so everything between 0 and 1, all of these points, okay, get mapped to a different value in the kind of our multivariate normal. So each one of these, if we generate the same value for one of our uniform, we see, and we go up and down in the other thing, we see it's just we're going around the circle here, okay? We're just moving around the circle. And on the other hand, if we stay in one location in the other direction, we keep the same theta angle, but we move farther away from the origin if we do it this way. All right, and so this is the Box-Mueller transform, and it's a way for us to generate values from a random normal distribution. And R doesn't actually use this. They've since come up with better ways of getting random normal values, but this was an important way to generate random normal values for a long time, and so that's why we bring it up. I'll post up some of the pages out of the textbook. This is from another textbook that talk about kind of the development of this Box-Mueller transform. Okay, so we'll end there. Have a great weekend, you guys.